Okay, everybody, so I'm going to talk to you a little bit today about atomic structure and sort of introduce some of the history to you. One of the things that I like to ask students when I'm doing this in class with them is, well, what are we made up of? What are we composed of? And so what I would like you to do now is using all of the knowledge that you have from your past science experiences, and this goes back to 7th grade, and even maybe earlier, what things or what do you think we're made up of? What's the smallest possible thing that you could describe that a human or that the world around you is composed of? And tomorrow we're going to discuss this slide. So take a minute, pause the video, and do that. And tomorrow we'll go over that together. But what I also want to talk to you and give you about, information about in this video is the history of the atom. And so when we look back, and we go back a long, long time ago, because the history of the atom and the models that we have, they were made up over a long period of time with many, many scientists working on this. So we go back to early Greek times, Democritus, and this is where the first concept of an atom is developed. The idea is that matter is composed of these tiny particles. The problem with this type of model is that there's really no empirical evidence to help describe what's going on. So although you can have this conceptual approach and say, yes, there are atoms. In fact, atomos is the Greek term for, indivisible. There's no real experimental evidence. The technology just wasn't there yet. And so what followed a few hundred years later was John Dalton. And what John Dalton did was he came up with the first experimental working model of the atom. And there were really two main things that he pulled upon in order to come up with his model. And one was called the law of definite proportions. And the other was the law of multiple proportions. And what the law of definite proportions says is that if you have a compound, like H2O for example, and he was doing this with masses, he would notice that H2O always had 16 grams of oxygen and 2 grams of hydrogen. And no matter where the sample of water that he would use, when he looked at the grams of oxygen and hydrogen, he would see that, in fact, there was always this set definite proportion of mass between oxygen and hydrogen. And this was actually done by a different scientist. Dalton didn't experimentally do this. But something that he did work closely on was law of multiple proportions. And what this law said is that when you have different compounds, the elements can combine in whole number ratios with different multiple proportions. For example, you could have NO2, you could have N2O, you could have N2O5. Notice that they're always whole number multiples of one another. And what this evidence showed him was, first of all, that atoms, they are composed of indivisible, solid, hard spheres. If you have a particular element, all the atoms of that element are identical. So atoms of a particular element are identical. And you can combine these atoms to form compounds. And so if we were to draw, well, what would Dalton's model look like? If we had to draw a picture of it, well, we would have a solid hard sphere. And we would just color that in. There's nothing inside this sphere. You can't break it down. It is what it is. There it is. It's set. There's nothing smaller. Now we know that this isn't true today. We know in fact that there are smaller particles, things that are inside the atom. And so that's when our next scientist comes in, J.J. Thomson. And J.J. Thomson, a lot of scientists at the time were working with electricity. It was, the new thing to work with. And people were applying it to matter to see how electricity would affect matter. And so what J.J. Thomson did, using something called cathode ray tubes, was he discovered the electron. The electron he discovered to be a small, negatively charged particle present in all atoms. So imagine that you have this particle that's smaller than the atom itself. And all of the atoms that you test actually contain this small particle. How small are we talking here? We're talking about a particle that's about 1/2000, 1/1836, the mass of a hydrogen atom. So that's a particle that is much, much smaller than the hydrogen atom itself. And that's really, really fundamental because what we see here is that there is something smaller than what Dalton was describing as a solid atom. And so if J.J. Thomson were to draw a model, which he did, it would kind of look like this. If we were to draw the J.J. Thomson model, we would still have, a circular atom. But now inside that circular atom, we would have particles that were smaller. We would have this positive and this negative in there. Now, even though J.J. Thomson didn't directly discover the positive particles that are present in an atom, he still knew that they were there because atoms are neutral. Now, he called this model, he called it the plum pudding model. It's British. So plum pudding is a dessert. Why not name things after desserts? Google does it with Android. J.J. Thomson started the trend back in the 1800s with his plum pudding model. So look at how we've progressed here. We go from Dalton, who had this solid hard sphere, and now we have J.J. Thomson, who's discovered something smaller than the atom itself. Well, what was the experiment that J.J. Thomson did to figure this out? He used something called cathode ray tubes. And a cathode ray tube, and I'm going to show you this in class, so please remind me, say, I want to see the cathode ray tube. We have one of these. And I'll describe the experiment again in class, but here is my metal over here. I'll highlight it. And when we pass electricity through the metal, there's this beam of particles, which looks like a beam of light, that comes off of the metal. And what's interesting about this beam of light, or actual particles, is that it comes off of pretty much any metal that you put in there. And you can actually get the beam of light to bend, and we can see that down here. Let me just make this a little bit smaller. We can see this down here. When they put a magnet, and I'll do this in class again, I can get the beam to bend. And that tells me right here that the particles are charged. And we can see that again if I do an electric field, that the beam will also bend, and it's attracted to the positive pole. And because it's attracted to the positive pole, that means that the particles are negative. Now, this is just a summary of all of what I said in the last two slides. So just to summarize this, J.J. Thomson discovered the first subatomic particle. He changed the model of the atom forever. Something that J.J. Thomson said was that in this plum pudding there's a uniform
distribution of charge. And we know that this isn't true. So if we look at the next model of the atom in a progression, it was done by a scientist called Ernest Rutherford. And what Ernest Rutherford added to the model was the following. He said, there isn't this uniform charge. We don't have a plum pudding model here. That's not what's occurring. What we have occurring is a separation of charge. He said that the positive charge is found in a small, dense, central region of the atom. And today we know this as the nucleus. And then he said that the atom is mostly empty space. And this is occupied by the tiny electrons. So, if I were to draw a model of his atom, we'd have, instead of the uniform composition here, we would have a small nucleus. Then we would have outside the small nucleus these electrons. Outside of the nucleus, it's mostly empty space. Now, what experiment did Rutherford do to figure this out? He did something called the gold foil experiment. And this is by far the most popular experiment that is asked about. And I think so because it really revolutionized how we look at the atom. It's the first nuclear model. So if we look at this diagram carefully on the left, it says, here's the hypothesis, the expected result based on the plum pudding model. What Rutherford did was he shot alpha particles, which I'm highlighting right now. Alpha particles are radioactive particles that are positively charged. You can think of them as a positive stream of particles. What Rutherford expected, if he was, confirming the plum pudding model, is that the alpha particles, I highlight it again, would go right through the gold particles if they were this uniform composition. But what he got from his experiment was something very different. What he saw was that, and we'll do a different color here, what he saw was that these alpha particles, they would go through the gold foil most of the time. But occasionally, the alpha particles would hit something in the gold foil and they would bounce back. Or they would be deflected. The fact that the alpha particles were hitting something in the gold that was causing them to ricochet, to either deflect or bounce back completely, meant that they had to be hitting something extremely positive inside of the gold foil. And when they hit that something positive inside of the gold foil, they were repelled by that positive center. And so what does his result show? Well, what it shows is this. If we look over here, the alpha particles would go right through and they would pass through the empty space of the atom. But every once in a while, an alpha particle would hit something very massive. The gold nucleus has 79 protons. 79 protons is a lot. It's a big positive electric field right in the middle of the gold foil. So those alpha particles would hit that nucleus and they would deflect. Now I'm going to show you a great video on this. Modern science sort of recreating this. And we'll see that in class, and I'll post it on iTunes U as well. But these are his major findings. Most of the atom's empty space. There's a small region of the atom, which is the center of the nucleus. It's positively charged. It repels those positive alpha particles. Now, at this point, I'm going to stop the video. This is the early history. It goes through to where the nuclear atom is developed. But what we're going to do in the next video is sort of take a break from this. And we're going to talk about, what in physics, because really it was was physics that sort of propelled this, changed the way that we're going to look at matter and energy. There were some huge developments in physics in the early 1900s, and that actually led our way to knowing what we know about the atom, which is that it is much more complex and was originally envisioned. There are two more models to follow. There's the Bohr model and the wave mechanical model. But in order to really understand that, we're going to take a lot of time in the next video to go through some of the developments in physics. Alright, thanks so much for watching, and I have some questions that are attached to this, so please do those. Remind me about the videos and to show you the cathode ray tube, please. Thanks.